Hi, welcome back to the new week 9 doubt clearing session for aluminum based alloys and metal matrix composites. I am Ananya. I am a PhD student at Indian Institute of Technology, Delhi. So let's start today's session. This week lectures consist of the main topic of metal matrix composites. So these are the topics which were covered in these week lectures. The metal matrix composites, different types of processing of metal matrix composite, what is metal matrix composite, how it can be manufactured, what are the different process parameters for each type of processing, and then a little introduction to the particle distribution and particle bonding in case of the metal matrix composite. So first of all, I'd like to know if you have any doubt, and if you don't, then I'll go with my PPT.
No, ma'am. If you could start from the beginning and revise, so it will be
Okay,
helpful.
okay, no problem. So then we'll start from the beginning. So let's first understand that what is the difference between metal matrix composite and metal alloys. So can you please tell me what is your understanding the difference between these two?
In alloys, the individual components are, contributing to make a new set of properties, whereas in composites, the individual components retain their properties itself. Uh, that's the major difference.
Yes, you are correct. But in more layman term, what I can say is if this is one alloy, here are some grains, right? And these are the grain boundaries. So we have already been talked about grains and grain boundaries and so on. So if these are the grains, then in case of alloys, inside the grain, this will be the lattice orientation, and in this lattice orientation the solute atoms and the parent atoms both are present. So it will just look like this. If this is the matrix, if this is the parent lattice, then if these are the aluminum atoms, in aluminum the substitutional atom is also of same size and it will sit in the place of aluminum. So if it's one solute atom, so it will be present inside the lattice itself. There will be atom of the solute particles. There will not be any solute cluster. Yes, there will be, but that will be called as precipitates. Precipitates are some compounds. So precipitates are like, if there is one precipitate, so it will be like one lattice which is having the MgSi2 compound or lithium boron compound, those which are known popularly known as the precipitates found in aluminum alloys. So this is an alloy. What is metal matrix composites? Again, this is alloy. This is MMC. Here, if these are the grains of the aluminum alloy, and if suppose in AL, just say 8082, I have taken, this is one heat treatable alloy, na? So if I am taking this aluminum alloy and I am mixing with SiC, what will happen? The SiC will sit in the matrix. These are the SiC. They are not bonded with the aluminum. They are not present inside the aluminum lattice. In alloy, the lattice of each grain was consist of aluminum metals like the parent metal and the solute atoms. But here there are no solute atoms. The solute atoms are present inside these type of grains. These are aluminum grains and these are the SiC. SiC here it will be called as reinforced material or particle. This is why MMCs like metal matrix composites are also known as particle reinforced metal matrix composite. It's also called as particle reinforced composite, or particle metal matrix composite, or aluminum matrix composite, aluminum particle reinforced matrix composite. These are some names given by different researchers to the different types of metal matrix composite of aluminum alloys. So in case of aluminum alloy, there are solute atoms present in the lattice, and in case of metal matrix composite, these are the aluminum alloys, but inside this aluminum alloys there are some separate sitting or separately seated SiC or ceramic or any other type of particles which are not bonded with the lattice of the parent metal. So these two are very much different, the alloy and the metal matrix. So this is the main concept of metal matrix composite. So as a result, what happens is, here if this is one Si, now the property, the exact property of Si or the exact property of aluminum cannot be achieved here. There will be a mixed up of aluminum and Si properties. But here, as this is separately seated, this is why the property, the individual property or individuality of the parent lattice and the SiC or the ceramic or the reinforced particle will be maintained. This is one major difference between alloy and metal matrix composite. So this is why if the SiC or the ceramic is seated like this, so this interface is a critical zone, because there it was bonded, there was a bonding between each atom. Even if there is any breakage, any fracture due to some external applied load, the fracture will take place in the grain boundaries, because grain boundaries are the most energized zone. There the bonds are either stretched or compressed, so this is why they are feeling more stress, and this is why these bonds are having this grain boundaries are having the most energy, high energy zone, and the fracture will take place in the grain boundary first in case of alloy. But in case of this thing, the fracture will take place in the interface. Because this interface is not properly bonded as like in case of alloys. So this is why there is something very separated. This SiC or ceramic, or I won't say SiC, I will say particles. The particles are separately seated in the alloy. So this is why the interface is the critical zone, and the interfacial bonding, the distribution of ceramic or the distribution of the particles, and these things are very important. So there are two major aspects in case of MMC. One is the distribution of particles, and another one is the, as was said in the lecture, the weighting. I'll say the interface or interfacial bonding. Other than that, weighting you can also take it as a separate entity, weighting of particles. So this is why each time you do not need to melt the particles. This is very important. There are one phase, two phase, three phase, whatever type of processing of MMCs available. But you should also remember that particles not need to be melted, because particles will just sit. So this is why if we are just adding some particles in a melted metal, it will form as a metal matrix composite if the particles are not getting melted, because if they are getting melted, they will be they will participate in the alloying, they will make some bond with the aluminum, or they can be seated in the lattice structure of the aluminum itself. So this is one important thing. So let's start from lecture 1. So the term composite broadly refers to a material system which is composed of a discrete phase, which is called as reinforcement, distributed in the continuous phase, which is called at as the matrix, and which derives the combination of properties not attainable by the constituent individuals. So it's like in case of MMC, we can have the individuality or individual property of the particle and the matrix, and at the same time, due to the distribution, interfacial bonding, weighting, and the interface energy, there will be combination of properties as well. So we can get the thermal conductivity, electrical conductivity, strength like the metal, and at the same time higher strength modulus, low thermal expansion, wear resistance, this type of properties of the ceramics or the reinforcement particles as well. For aluminium, as aluminium is known for its low density, so we can get very low density in case of aluminium metal matrix composite, because you can imagine we are adding some extra material in the parent metal, so obviously the density will increase, but as already the aluminium is so low density material, the AMC or the MMC of aluminium will not have much more density or a bigger density value like the other metallic MMCs. So the processing of MMC include three types. Uh, One is solid state, liquid state, and the vapor state. So there are different processes available under this three state of processing of metal matrix composite. It can be like solid state of the both particles. It can be like liquid state where we are just gonna add some liquid or semi-liquid. We are gonna add the particles in the liquid metals or matrix, or we are going to just add some semi-liquid particles in the liquid matrix. And in vapor phase, we'll process the metal matrix composite in the vapor phase. Next is the stir casting. So stir casting, it's a liquid phase, because stir casting is also used for normal aluminum alloy making. So if you can remember, in the case of aluminum silicon alloys, there was one topic like the primary silicon growth, the twin boundary effect, and the undesirable growth of the silicon in the direction of the twin plane. There, strontium, barium, and sodiums are generally mixed with 0.02% in the aluminum alloy to control that Si growth, which is not needed, and to alter the Si growth region or the plane. So there, steel casting is also used. So at the time of steel casting, what happens is there will be a container in which we put the aluminum blocks. After heating up, this aluminum blocks will be melted. The shaft connected with the motor and the impeller will be dipped inside the aluminum melted alloy, if this is the alloy. Then there the strontium, barium, sodium, any one type of the elements are mixed in the alloy, those will be melted inside the melted aluminum, and they can restrict the growth, undesirable growth of primary silicon. In case of MMC also, this stia casting can be used. So there we can add some powder of the ceramic or the reinforced materials just to get the MMC. So at the time of stia casting, you have to be very careful. The reinforced particles should not get properly melted, otherwise they can form alloy. So even if they are getting melted, you have to supply some other external reagent which can prevent the formation of alloy instead of metal matrix composite, because we want to make MMC using the stia casting. So the process is simple. So these were some examples drawn at the class, that the matrix can be of aluminum, magnesium, carbon, sorry, iron, copper. Then it can be either, and the reinforcement particles can be inorganic or organic. In case of organic, it can be just red mud fly ash, but in case of inorganic, it can be oxide, nitride, carbide, boride, or something else. So there are some popularly used reinforced particles which are often mixed with aluminum alloys. So there you will find TIC, titanium carbide, and silicon carbide. These two are the most commonly used ceramic, or you can say reinforcement particles, often mixed to make the metal matrix composite. Other than that, this TIN, BN, and Al2O3, SiO2, these are also mixed. I have found a lot of paper on this type of metal matrix composites. There are various route of making or processing. We'll go through one by one. Before that, this was the design of the shaft impeller things used in case of stair casting at the time of lecture. So a three-bladed propeller can be used. Four-bladed turbine can also be used. These are some possible arrangement for stair casting. The next was the process parameter of stair casting. So yes, it's obviously very important that how much length you are dipping inside the material, because this is a hot material. So obviously it's very dense, and it's very critical as well. This impeller shaft should have a property, or should have a very high melting point. Otherwise, it can get melted at the time of steering. This is the motor, and this is the melted aluminum. So, if we are dipping this shaft very much inside the melted aluminum, what can happen is this motor will feel uh, like it will be hectic to rotate this impeller, because it's been dipped inside the aluminum very much. Also, it's if it's not dipped very much, if it's in this range at this position, then it will not have that effect of the steering. It will not serve the purpose of actual steering inside the metal, because the steering is very important. Otherwise, the mixed up particles may get agglomerated, or just may get melted if they are having low melting point, or the particles can just stick into the wall of the mold. So these are some typical problems seen in case of this type of MMC processing. So steering speed is also important, because the steering speed should have an optimal value, because it should not happen that the steering speed is so low that the proper mixing is not taking place. The particles are getting agglomerated before being steered, and also it should not be very high that there will be a turbulence in the melted aluminum. Accidents may happen. So these are some precautions. And the process parameter, the dipping length, melt temperature, pouring temperature, all the things are important, because it should not happen as well that we are keeping the temperature for longer time, because we have to keep the temperature for certain time to just get much more good, what's it, a better adhesion or a better weighting of the particles in the melted aluminum, but it should not be so long that it will just degrade with time. So the advantage of this type of processes are, if there are already available so much available setup of stair casting. This is a very well known process, so simple, and the cost is also not that much in case of stair casting. But the problem is this impeller design is a problem, then this deeping length, etc. process parameter you need to be concerned about, and the number of particle mixing will also be a problem, because the stair casting cannot result in a near net shape. If you are making such type of molds in which you are mixing, you can get some near net shape, but you can imagine if I want to get this type of structure, you cannot make a mold like this and then you are deeping the impeller here and it's rotating. It may just damage the mold. So the near net shape cannot be achieved. That is a problem. Clustering, settling down, particle rejection, low weighting is also some problem related to stair casting. And also there is one another problem, because at the time of pouring the particles, it will be open to air. The melted aluminum will be open to air, and from normal environment we are just mixing or pouring the particles. So that may introduce some gas porosity. So that is one another problem regarding stair casting route for MMC formation. So the next type was melt infiltration. So in case of melt infiltration, what is happening, if, as I said, this is one mold, if I want to make this type of structure, I'll just put some preform of the particles. Preform means a porous particles. It will not look like this, but instead it will just do you know what is lattice structure in case of normal design? Any one of you know what is lattice structure? Did you see ever the lattice structure? No one?
Ma'am, isn't it like the ordered arrangement of atoms? Is it?
Yeah, lattice is the ordered arrangement of atoms, but in case of, what should I say? Instead of a solid block, if I'm making some lattice structure, it will just look like this. It will reduce the material and the time of making and those properties, high strength and this type of
Yes,
things.
ma'am.
So okay,
I
this,
have seen.
yeah, you have seen. Okay. This sort of things are called as lattice structure. So these features now are very small. It's not this much big what I have drawn. So these features are very small. So there is something like I have introduced some gases or some air pockets in a solid 100% infill part. This was 100% infill part, means this is the part density is 100% density, but here the density is reduced to 50%, let's say, let's assume. So nothing like I have introduced some air pockets in a ordered manner. So that is what lattice is meant, and lattice concept is uh, have come from the lattice of the atoms, what you have said. So, like those lattices, if you can make the preform of the reinforced particles, you can just pour it, you can just place it in the mold, and now you, uh, what's it? You just pour the melted aluminum in it. You just pour the aluminum, melted aluminum here, and it will be poured all over the structure, and the preforms will be there, which is acting as the re- reinforcement particle, and the melted aluminum will fill the rest of the vacant space. And this is how you can get that metal matrix composite, and this technique is called melt infiltration. So this is what meant by the melt infiltration. Next is the squeeze infiltration. So it's there is one thing is quiz casting, but it's different than that. It's like after making this, now there will still be some air pockets present in this mold, because I'm just pouring the metal aluminum from one side or maybe two or three sides. But there all over the mold, the preform is present, and you don't know about how much gap in between the preform. It may happen there is some micrometer or millimeter gap in the preform. The pores present in the preform is just a few micrometer or millimeter. Then for filling those small air pockets by melted aluminum, just by just pouring it from outside or externally, is difficult. So you may not know the pouring is done properly or not. It may happen that there will be a lot of air pockets still present after pouring the melted aluminum. So what we do for that? We go for squeeze infiltration. There we just press the thing, we just apply some hydraulic pressure onto this type of mold, so that all the things, the peeling of the preformed pores by the melted aluminum should take place properly. There should not be any air pockets left after the pouring process. So that is what meant by squeeze infiltration. So the advantages are near net shift products with selective reinforcement. Obviously, as I said, in case of stir casting, you cannot make the mold and you cannot stir the things inside the mold. But here you can stir the things. You are not supposed to stir the things. You just pour the things in a proper mold. So it's good for the near nature manufacturing of MMC. But the problem is we are just placing the preform inside the mold. So they should be self-supporting. Means MMCs can be many types. I'll talk about that. But before that, you have to place the reinforcement particle in all over the mold. If you want to have some certain portion of this mold, I want this portion of the mold as MMC and this portion of MMC, then I have to place the preform in this portion only. And this preform should sit in this portion without any support, because I cannot provide any support externally. There will be a problem. So this type of problems are there regarding the melt infiltration problem, but otherwise it's good process if you want to make a uh, uh, proper component with an MMC material. The lecture 2 covered the spray deposition. Again, it's a very,
Ma'am,
yes,
what are the criteria to ensure that this wettability of this preform happens?
wettability of the preforms happen. Okay,
Yes.
in situ processing, I think in situ is not possible, because you are just pouring the metal inside the mold. But ex situ, like you can go for the SEM EBSD after that. There only you can see how much weighting has been taken place.
Mom, like, isn't there any way to start it like with maximum, you start it with only maximum, ensure with the process that this is the best for wettability.
Okay. So there was the equation for wettability, na? In case of the other processing, I think in case of the two phase or something, na? But the
Yes.
weightability you cannot derive beforehand. You can only see it after the processing, because this type of process, I'm talking about this type of a melt infiltration, na? For stair casting, you can optimize the steering speed or the dipping length or the impeller design. But in case of melt infiltration, you cannot optimize the process parameter, because there are no such process parameter by which you can control the weighting. You can just see how much weighting is taking place after the process is done by some SEM and EBSD, and according to that you can optimize the reinforcement particle distribution inside the mold, because you have to place the reinforcement particle inside the mold, and you can optimize the uh, pouring time and the pouring velocity, in which speed you are pouring the metal, how much temperature you are keeping in the poured metal, and how much temperature you are keeping in the mold, how much cooling you are providing to the mold. This sort of process parameter you can look after. Otherwise, uh, beforehand you cannot determine.
Mom, during the making of the preform also we can't help.
Yeah, making of the preform, that's different thing now. The in case of stair casting, you are pouring or you are adding the particles. The particles can be spherical, but most of the cases they are not spherical, they are somewhat with very irregular shape. So if you want to so you are adding the irregular shaped reinforcement particles in case of stair casting. So there you can determine the um, weighting with respect to the particle shape and size. But here in the mold, you are placing the material, you are placing the particles. So there you need to, according to me, you need to make some this type of lattice structures, and there you can use the surface type lattices instead of some rod type lattices. So it's basically uh, in a mold now, you have to, this is the mold, you have to place the SiC particles, for example. So you can just make the SiC particles spherical or plate like structure instead of some irregular structure. But anyhow, you have to place it with the help, without any help of supporting structure. So they should have the self supporting structure like this. Otherwise they cannot be seated there na, because this is a picture where I'm showing a 2D image. This will be stacked like this inside the mold, and this is where the aluminum metal will be poured. So do you understand what I'm trying to say?
Yes, mom, I'm able to understand.
Okay. So this is why you can, like, it's not like you cannot determine, but you can play with the SiC or the reinforcement particle shape and size. But here you have to have a lattice type structure, a preform, porous preform. Otherwise, uh, नहीं तो you cannot place the thing inside the mold. So there is one restriction in case of melt infiltration. There is one restriction in case of stair casting, that you cannot get near net shape. Here you can get near net shape, but you have to then play with the lattice structure or the porous preform that you are going to place inside the mold. So that's all. So yeah, I was talking about the spray deposition. So in case of spray deposition, what happens is there will be some melted metal, I'll say aluminum. This aluminum will be passed through this nozzle due to the large pressure and gas flow and all the other things. This melted aluminum, when it's just dipping drop by drop from this nozzle, it will be atomized. Atomized means now the aluminum atoms are separated. These dots are some aluminum atoms, which is meant by this atomization. So these are some aluminum alloys or atoms of aluminum, and there is one substrate. Substrate means onto which you want to deposit the metal matrix composite. When this atomized these things are coming, you can just add the particles there. The particles will be mixed with this thing, and the whole thing will be deposited over the substrate. So here all things can take place easily, but the only problem is you have to have a substrate. You cannot get the near net shape anyhow, and over this substrate this deposition will take place. So if you want to have this thing separately, you have to cut the thing from here, from the substrate, so there will be loss of material in case of cutting. And also sometimes you do not want to go for a component which is fully made of MMC. Instead you want to have the component which is coated with the MMC. There you can use this type of spray deposition, or there is one another vapor deposition commonly known as PVD, physical vapor deposition. There you can go with that. So the thing I was talking about is MMCs can be of different type. One type is there are metal MMC, a polymer MMC. It can have this type of sandwich structure. Okay, so it's like here one fibrous thing is present which is called as reinforced material or particle, and this is the metal. This will be called as MMC. The second type is the whole material is made of MMC. There the particles are sitting separately and making the MMC. The third type is there will be a substrate onto which the MMC will be printed. Okay. And the fourth type is there will be the sheet. I am showing you the top view here. The fiber type of this MMCs will be fiber type of what say reinforcement particles will be added, or reinforcement fibers will be added. So these are some types of MMCs. Here it can happen that this is the polymer and this is the metal, and inside that there is another type of polymer, or this is the polymer and this is the metal again. This type of sandwich structure can also be called as MMC. So the first type of metal matrix composite which came into the research world was this type of sandwich structure. After that, researchers invented this type of overall mixing of reinforcement particles inside the melted metal. The composites uh, is the well-known composites are made up of polymer only. These days, researchers are trying to develop the metal matrix composite, because mixing some reinforcement particle in the melted metal is a way tougher than polymers, because there is a certain high temperature of melting, or high temperature of the for the metals, high melting point of the metals that can melt the reinforcement particles as well. So you have to be very choosy in terms of the particle and the metal combination in case of metal matrix composite. So the next process was solid state method. This is the type of solid state method. There you can use the powder metallurgy. It's like in a plate you are just spreading the powder of one type, then you are spreading the powder of another type, and then you are just pressing it using some hot isostatic pressing, and you are getting one composite layer over a substrate. It's simple, but again it's not that much effective because there is no melting of the metal. So the interfacial energy and the interface between the particles and the metal powders will be a critical zone for the fracture, and fracture can easily take place there. So that is the solid state method. Then high energy high rate process. So high energy can be provided by some mechanical or electrical means, and rapidly the high energy can be provided, so that will be called as high rate. So there you are just with a rapid speed you are providing some high energy onto this type of uh, solid state processing, and you are getting some MMC. There you can just control the microstructure because you are providing the energy, so the melting will not take place, but all the atoms of the metal will be energized, and there will be some uh, temperature gradient and some heat flow, and these things will be for very short time of period, and this is how you can control the phase transformation and the microstructure basically. So ALSIC is a well-known composite made of such high energy, high rate process. Then there is another process which is diffusion bonding, as I already have shown here, fibrous kind of thing. So you are just adding some fibers of the reinforcement material instead of particles, and these fibers are having long interface between this fiber and the metal, and you are just pressing it, or you are just making this type of sandwich structure. That is one example. In case of aluminum 6061, boron is used in the form of fiber to make the fibrous type of MMC or AMC. Then comes the
Uh,
whip. Yes,
Excuse me, ma'am.
yes,
Ma'am, I'm having doubt regarding when we are discussing about the phase transformation and grain growth, right? We are
yes,
just restricting the phase transformation and
yes,
the grain growth, right?
yes,
So, take example in case of steel casting, as we already discussed, because of the formation of
yes,
dendritic structure. So there will be a chances of nucleation as this particle is solid suspended particles, right?
yes.
So how this will ensure that there is no transformation means how to get about these ideas means there is no grain growth during this stair casting means I
So
want to know.
phase transformation doesn't only mean the grain growth and the nucleation. Phase transformation means you are having the material at a particular elevated temperature. If this is one temperature graph, so you are having at this temperature right now, which is a high temperature, and now you are cooling it down to this temperature, or you are holding the material here and then cooling it down, and this is how the phase transforms. Phase transform means in case of aluminum it's very easy because for aluminum there is no such phase. There are some precipitates which make some phases, but in case of other metals like iron, like I know the steel, which is iron carbon diagram. If you see, there are martensite, austenite, bainite, perlite. So there, how the Fe3C particles are arranged, how they are growing, and depending upon that, the phase transformation takes place. But in case of aluminum, there will be some precipitates already present inside the alloy, and how the precipitates are moving in between the alloy, how they are making some arrangement in between them. Depending upon that, you get some phase transformation. And if you want to control the phase transformation, so obviously you do not uh, allow the high temperature thing for higher time. There will not be any phase transformation. You can control the grain growth. Obviously grain growth will take place if you are allowing the holding the material for longer time at an elevated temperature, है ना?
Okay, yes, ma'am. Means we are not providing the proper time. Means
Yes,
we are not providing
it's
the
high
time
rate. Means
to have a grain growth.
you are providing some high energy in terms of mechanical or electrical, but you are not keeping that high energy for longer time. You are suddenly removing the energy, you are suddenly providing the energy and removing the energy, and this is how you are providing the energy to get the proper interfacial bonding between the particle and the matrix, but you are not allowing the aluminum metal to get some grain growth and the phase transformation. As simple as it is.
Okay, yes, ma'am. Right.
Okay. So the next is the vapor state process. So it comes with the popularly known method, which is physical vapor deposition, also called as PVD. There you will just supply the material in the form of vapor, and the vapor will be deposited over the substrate. Vapor means nothing. There will be one target material, some electron beam or some plasma or some just ionized gases will be provided that will hit the substrate, the target will release some atoms or vapor of that particular target, and the vapors will get deposited over this material. And if you are mixing the particles as well with the vapor, there will be some MMC made over the substrate. So this is the physical vapor deposition used for MMC. Normally, PVD is used for making some kind of thin layer or thin coating over the material. Like if you want to get rid of rust from iron, you can have thin layer of some other components over the iron, and that thin layer or thin coating can be got by PVD. But here you are using this process for making MMC. Advantage is wide range of matrix composite can be used, because for aluminium you can easily melt the aluminium and add the SiC, TiC, TiB boron, because aluminium is having very low melting point, and the other materials, ceramics and other alloys, are having higher melting point. So the other metallic alloys or ceramics or carbide borides will not get melted in the aluminum. You can easily get the metal matrix composite. But where the metal is having higher melting point, and the ceramic or the reinforcement particles which you are mixing are also having higher melting point, then at the time of melting the metal, the reinforced particles can also get melted. So there will be a problem. To get rid of that problem, you can just use this type of PVD method, where you are just vaporizing the material, not by heating, by heating with some electron beam. It's like not by heating, rather heating with electron beam or some ionized gas or some plasma, etc. So the next process is the two-phase process. So two-phase process is nothing but where what we have discussed till now. There, if you are mixing two melted things, those type of things, but normally two-phase processes are used, because you do not need to melt the particles. So what you can do is, you are having the metal, melted aluminium, you just reduce the temperature of the melted aluminium, so it will have some starting of solidification, and at that time you add the particle, and both the things will get uh, deposited over the substrate, and it will be called as the two-phase processing. So two-phase processing means the matrix is coexisting with liquid and solid phase at the time. So there was one example of variable co-deposition of multi-phase materials, VCM, where you were just allowing the melted things come from a nozzle, and you have reduced the temperature, so these things will be solidification, starting of solidification. There you are just adding the particles, and this whole thing is getting deposited over this substrate. This thing will be called as two-phase processing. The main advantages of this type of thing is, again, you can control the microstructure, because there, if you are depositing some melted aluminum, na, there will be one problem is, in case of the solid state, as you have seen, you can control the phase transformation by controlling the grain growth. So you are basically controlling the microstructure. So here also, as you are not holding the material for longer time, under elevated temperature, the microstructural issues can be resolved. You can control the microstructure. So you have seen that some mushy phases are made, which is consist of solid and liquid coexist phase, and this will result in the equax microstructure. So there will be some breakage of the dendrites. Why the dendrites will form, we have already discussed. When there is some melted aluminum or melted metal, it's solidifying due to the which type of cooling, super or under, the dendrites are formed.
Because of supercooling.
Yes, because of the supercooling, the dendrites are generally formed due to the temperature gradient between the interface of the solidified protrusion and the melted metal. And these dendrites grow with time in the melted region, and due to the effect of shearing or external forces, or due to the reason, due to anything, due to nothing, the dendrites may get broken, because those are just expanding their arms in the melted aluminum. So due to the melted aluminum temperature gradient also, they can get broken, and those things can be controlled in case of this two-phase process, because we are just controlling the temperature, because these all things are dependent upon the temperature. And if somehow we can control the temperature, we can control the phase transformation, dendritic growth, microstructure, everything. So here the main advantage is equiax grains are formed uh, rather than the dendritic formation. It's called the thixotropy. There was another example of Rio casting, when actually melted and two-phase things are stirred, and similar dendritic formation was taking place, and those are broken, and equiax microstructure was achieved. So these are the two most common example of two-phase processing. But other than that, also there are many other. Some of you are also working in additive manufacturing, and you can also see there, in with the use of additive manufacturing, you can make the MMC, where you can coexist, you can make the coexistence of liquid and solid, of the melted, of the metal and the particles. When particles are added externally, in case of two-phase process, it will be called as ex situ process, what we have seen right now in case of VCM. But it can also happen that in situ processing we are doing to get the particles. So we will just mix some other reagents or some composition, different composition of different salts, and they will form the actual reinforcement particle inside the melted aluminum itself, or we'll just make it and then we'll pour it. So what will be the result? At the time of pouring, in case of X2, there can be some gas entrapment and those type of issues related to that. But here we can get rid of those issues of gas entrapment and the pouring defect, some pouring of inclusion along with the main reinforcement particle. So here we are just adding some salts. In case of TiB2, we mix KBF4 and K2TiF6 to get the TiB2. The other components or compounds which are formed, we can uh, just separate it out as a slag and just remove it to keep the TiB2 only in the melt, and that will give us a good reasonable property of the metal matrix composite that we are aiming for. So TIC, SiC can also be formed using the same process of this type of in situ processing. So this was done up to lecture 3. If you have any doubt up to lecture 3, you can ask. No? Okay. So from lecture 4, the weighting of the particles with the metal matrix was discussed. Weighting is important because the particles need to sit over the melted aluminum. So if there is the solidified aluminum, some if this is one solidified aluminum, over this solidified thing, a particle will get seated, and how it is seating, depending upon that, the properties will be affected. Because as I said, the interfacial bonding and energy is very important in case of metal matrix, because you can see there is no such bonding, lattice bonding of the particle and the aluminum. So whenever you will apply some external load, it will directly go to the interface and it will start the cracking from the interface. It will attack the interface and try to deattach it. So this is why the weighting is very important. Weighting means how much surface area is there in contact with the metal. How much surface area or of the reinforcement particle is there in contact with the metal. So that will be determined by the angle, which is called the weighting angle, or we can just, as someone said, as Vanshika said, that we can just play with this angle to get good weighting, because we want this angle to be very low, otherwise there will be separation of the particles from the metal matrix. So some equation related to the things, where if this is the particle which is seated over the solidified aluminum, this is the angle theta. This is very important. Theta is the most important factor, because there are some surface energies related to this interfacial sitting, and this surface energy will determine how the particle will get seated over the solidified aluminum and how much surface area of the particle will be in contact with the metal. So this was all about the weighting of particles in the metal. The next topic
Ma'am,
was, yes.
excuse me, ma'am. Ma'am, here I am having doubt. How we are getting this? direction of the surface energy, like gamma SV is in left direction and gamma SL is in right
Okay.
direction, like this.
So if this is seated over here, so if there is some, so this surface energy is also like considered with this origin. We are taking this origin. This is one particle which is seated and this is our origin, and here if we draw the vector or the direction of the surface energy, it will look like this. So it will be like, if this is the particle, the surface energy from this origin will be towards the particle, because there will be the surface energy related to SL, means solid and liquid. Here it will be away from the particle because there is no liquid, and here it will be towards the particle. Obviously this is simple, this is the weighting angle, so this will be in this direction. So it's basically how the particle is experiencing some energy towards them, towards in the outward direction, and with the weighting angle. So weighting angle thing is clear na, this is simple, this one is simple na, that how there is how much surface area is related, is in contact with the metal. If this is the surface area, this is in contact, so the angle will be like this. If this is the surface area which is in contact, then this thing will be much more than 90 degree, this theta will be more than 90 degree. So this is the angle between the, or this is the, this direction will depict about the surface energy towards the liquid, how the liquid will get seated.
Yes, ma'am. And how this gamma LV, surface energy of liquid vapor,
So
decides the
it's
surface
like
tension?
if there is one solid surface and the liquid is seated, so here there is air. Okay, so there is the vapor of this liquid, you can say. Vapor means how much atoms are getting ejected from this surface, and the air is also just putting some pressure over this solid. So how much air pressure the ejected atoms are experiencing, this is known as the vapor pressure. Okay, this is the common definition of vapor pressure. And if there is one liquid and solid surface, so obviously here will be vapor present over present. So the angle, this thing is clear. So it's like if this is the origin, because I have to take some origin to calculate the surface energy. So it is like towards the liquid, there will be some surface energy. Where the liquid is not present, outward direction from the liquid, there will be a surface energy. If you draw the curve from this side, you'll say this is the surface energy towards the liquid and the solid. This will be the surface energy for the solid and the vapor. Am I clear? Or
Yes, ma'am. Ma'am, actually, my question is another question is because of the interface, we are getting surface tension, right?
yes.
But we have the interface between like solid particle and solid vapor particle. That means the solid surface which is at left. So above this particle, there is a vapor, and at the interface, because the interface is dividing the vapor as well as liquid,
Yes.
means that's why we are getting surface tension. But in case of gamma SL,
Yes.
like surface energy of solid liquid interface, so is it not any surface tension present here, like at the liquid solid interface? Not
First
liquid
of all,
vapor, but liquid
we
solid.
are. Mhm. First of all, you have said that due to the interface, we are getting the surface energy. It's like due to the surface energy, due to the surface tension, we are getting the interface. Okay. The surface tension is playing the major role to get the interface. If the surface tension is very high now, there will be this much interface between the solid and the liquid. If the surface tension is not that much, then the weighting can take place. This angle will be much smaller than 90 degree, and the weighting will be very good. So this weighting is depicted by the surface tension of this liquid. Then this surface tension is also depicted by the vapor which is present in the outward direction. Because if this vapor which is present here is giving very much force over this liquid, then this liquid will try to shrink and the surface tension will increase. You understand what I am trying to say? You can tell me if you don't understand. I'll try to explain more.
I understood, ma'am. Actually, you said about the solid liquid interface. At the solid liquid interface, the liquid is completely weighted the surface. That means surface tension is very less. That's why we are having weighting. And because of the gamma LV means the surface energy of liquid vapor. So vapor is just pressing the liquid from means from top to down. So for that, it is having the large surface tension, right?
Yes. So when you see the rain droplets now which are falling from the cloud, why the rain droplets are circular or spherical in nature? Due to the surface tension of the water, na?
Yes.
Yes, so due to the surface tension, it tries to make or, or get a geometry which will be experiencing the minimum energy or minimum force given by the vapor or the environment. So this is why it takes the shape of the spherical or sphere. The similar thing here, if the surface tension is very much high, then it will not be getting melted, wetted in the solids. So this much you understand, that will help.
Yes, ma'am. I understood. Because it is because of the interface, because interfacial force is different.
Yes.
Because above is vapor and inside is liquid, so there is an interface that is forming.
Yes.
So because of that, I think surface tension develops, right?
Yes. Okay. So the next topic was the three stages by which the solid surface can be weighted and leads to the bonding. Right? Because at the time of normal casting or melt infiltration, you are just pouring the melted aluminum in the mold where the in case of melt infiltration, where the preform is present, the porous preform of the reinforcement particles are present. In case of stir casting, you are just adding the particles as it is. But if it happens that the particles are having some properties due to which it will not get that much weighted over the melted solidified melt or solidified metal, then it we can go for the solid surface, these three stages where we basically deoxidize the aluminum surface by molten aluminum, deoxidize the SiC surface, the disruption of SiO2 film, and weighting through the Al4C3 interface. So Al4C3 interface will help in the weighting of the SiC in the aluminum. But at the same time, Al4C3 is brittle in nature. I think it does have a hexagonal structure, but I don't remember clearly. But it's having the brittleness. So it will add a lot of brittleness in the aluminum SiC metal matrix composite as well. So if we are just incorporating some process in which the SiC is not getting that much weighting with the aluminum, then we can go for this three-stage process. Otherwise, uh, whenever you'll mix SiC with the aluminum metal, na, the Al4C3 will always get formed, and to restrict the formation of Al4C3, sometimes we add Ti in the melted aluminum just to get rid of this Al4C3, because Ti is having high tendency of making this carbide thing than aluminum. So the Al4C3 formation can be restricted. Otherwise, the or other way, the FTIC will be formed, by which the brittleness can be reduced. Because if we are not uh, we do not want, or we do not need that much brittleness in our MMC, so we can get rid of that brittleness by using the by mixing the TI. So the formation of Al4C3 is influenced by the alloying addition like Si, which can suppress it. So as I said, Si is also having high affinity like Ti of making carbide than aluminum. So Si improves the wettability by segregating at interface and forming strong chemical bond with SiC. So these are some important topics when you are dealing with a specific type of MMC. When you are concentrated upon the aluminum and SiC formation only, formation of metal matrix composite, then you can go for this Ti or Si mixing to improve the wettability. But these are not universal for every type of aluminum alloys. You have to remember this. Then metal coating on ceramic particles like Ni coating may also help. Exothermic reaction between the liquid aluminum and the metallic Ni films form the NiAl3, which will again help in our metal matrix composite formation. High temperature of the exothermic reaction eliminates the oxide layer. So dissolution of SiC and formation of Al4C3 is presented by the Ni coating. So as I said, these are uh, some specific examples of the specific type of metal matrix composite of aluminum alloy, specifically with SiC reinforcement, because SiC is the most commonly used reinforcement particle to get the AMC or aluminum metal matrix composite. So the next is the magnesium. Magnesium reduce the aluminum surface tension and alter the solid liquid interfacial energy, because if the surface tension is very much, then it can hamper the wettability. So magnesium help in that regard. Magnesium addition disturbs the oxide film on aluminum, lower the contact angle as it has good wettability with SiO2, which is presented on the SiC surface. So these are again some typical examples specific to one application, one metal matrix composite. Ti addition leads to absorption of the Ti and formation of TiC, which has better wettability. As I already said, silicon absorbs on the SiC interface and improves the weighting of the SiC by forming a strong chemical bond with SiC. So it's all about the weighting of the SiC, because one thing we have learned is the processing by which we can process, but this weighting is more important than processing, because anyhow by after making the metal matrix composite you can get the near nature thing by turning or something machining, but at the same time metal matrix composite machining is also a great issue, a big issue, because there are some interfacial particles being seated over the whole metal. Whenever you will try to cut the metal by using some tool, the tool easily get damaged by the cutting of the MMC due to this interfacial particle reinforcement. So that is also a big problem. Then comes the particle bonding. So the load is transferred to the stronger reinforcement via the particle or matrix interface. Therefore, the interfacial bonding must be strong. As I said, whenever you will apply some force onto the metal matrix composite, now the force will directly attack the interface. It will try to deattach the interface or deattach the particle seated over there. So the interfacial bonding is very important, and that depends on the weighting and the solidification conditions. Lecture 5 was different than the other lectures up to lecture 4. So if you have any doubt till lecture 4, please let me know.
Ma'am, which one has good wettability, Si and SiO2 particle?
So SiC is mixed, and in SiC you add the SiO2 what's it coating. So SiO2 is having much more weighting.
Ma'am, actually, it is because of the oxidation. So actually, Si particle, if we are adding from external, so Si is just get absorbed on the surface of
Yes.
SiC, right? So this is one case.
Yes.
And another case is if there is any oxidation, then SiO2 coating will be developed, right?
Yes.
So I am asking in which of these cases, means in one case we are adding Si, in another case we are having oxidation. So which of these two cases will be better wettability?
So the SiO2 will have, as you said now, for the oxidation. So the
Yeah.
SiO2 will have more weightability, but still I need to see it because whatever I think is SiO2 will be the answer, but I'm not 100% sure.
Actually, ma'am, in the lecture that I have seen these two statements. Like sometimes we are adding only silicon, and sometimes
Right.
we are getting oxidation, and then the layers are just make over the surface.
Yes.
That's what.
Yes,
Okay.
you are right. It was mentioned that Si is also mixed and the SiO2 coating is also mixed,
Yeah.
and both
Yes,
the
ma'am.
things improve the weightability. So which
Yeah.
one is better? So I
Yeah.
think SiO2 will be better, but at the same time, the oxygen there is SiO2, so the oxidation is taking place. So that can hamper the property of the SiC as well. So there can be the other problems.
Okay. And ma'am, if we are adding magnesium, that will reduce the surface tension of aluminum, melt aluminum.
Yes.
So if the surface tension is getting reduced, means can you tell me, ma'am, the mechanism of it, how it is getting reduced,
As
means
I said
what
now,
the
the surface
magnesium
tension. If the surface tension is low, means wait. It will
means, ma'am, addition.
come
How
in.
the magnesium is adding over there, and it is getting reduced.
Okay, magnesium will be added, just the magnesium
Yes,
particles
yes.
in the melted, and you see this picture. If it's having low surface tension, this thing can be made. If there is a high surface tension, this thing will be made. So the surface area which is in contact with each other will be reduced with high surface tension.
What else in magnesium that has this property? Means I'm asking.
Okay. So
Uh,
I really don't know the exact property of magnesium which is helping in this regard. So just normal literature review, I have gone through the things. I have also seen that Ti is mixed to avoid the formation of Ti Al4C3 because Ti is having high affinity. Like that only I know that magnesium reduces the surface tension of this thing, but I don't know
yes,
the
ma'am.
exact procedure. So if you want
Ma'am,
to know, I
actually,
can discuss in the next class.
sure, ma'am, sure.
Okay. So I have found another answer of your question that was raised in the last class about the non-heat treatable alloy. I don't
Yes, ma'am.
remember. You asked me the question.
Yes, ma'am.
Okay, so I have gone through some paper. I'll discuss after this lecture 5. Okay. Let me
All
first
right.
discuss about the lecture 5, then we'll have a recap. That kind of thing. So the lecture 5 was more concentrated on the distribution of particles with regard to the temperature field. So if there is a temperature field, means obviously if the metal is melted and it's getting solidified, and in the whole situation the SIC, why I'm saying SIC, the particles or reinforcement particles are just there seated in the melted region. So the distribution of this reinforcement particle may get hampered at the time of solidification, because the solidification will take place in this direction. Suppose at the time of solidification, we have seen, depending upon the time that we are keeping the material for the solidification or the temperature we are providing, there can be protrusion and the dendritic formation, and those can really hamper the distribution of SiC, because this if this is the wave front, which is, if this is the temperature front, this which is uh, moving from this direction to this direction for the solidification purpose, with the wave front, the or with the solidification front or the temperature front, the SiCs will just get, can just get agglomerated. So I will take an example of the sea. So in the sea, if this is the sea, the waves are coming. So the waves come, they just come like this, and then they move like in this direction. So this is the sand, okay, and this is the sea. The in the sea we often see the waves come, and then they move in this direction to meet the sea wave fronts again. In the wave front, if you throw a stone or a shell or something, the two things can happen. The stone may get dissolved inside the wave front. It will just go with the wave front only. Or if the stone is very weight heavy, then the stone will just get seated over the sand. It will not move with the wave front. Similar thing happens in case of the solidification. Solidification front means how the temperature gradient is moving, and along with that how the solidification is taking place. So with the solidification, there will be some wave front, and with the wave front, if the particles will just move, will just float rather, then they can get agglomerated in one position. At the end, what will happen, if this is the metal, these are the reinforcement particles, this is the direction of the solidification. When the solidification will be done na, the particles will be agglomerated in this position. So in the whole metal matrix, there will be some particles here seated over here only, and very less over here, and which is undesirable. So this is why the solidification front is also important. So how we are cooling it? We are cooling it unidirectionally, or from all the direction, or with high temperature high cooling rate, or low temperature cooling rate, what will be the same? Depending upon that, the solidification front will be present, and also how much is the thermal conductivity of this reinforcement particle and the metal. Depending upon that and the ratio of that, this agglomeration or the engulfing of particles will be decided. So this was shown. So I'm just using this page. So alpha was the thermal conductivity of the particle to the thermal conductivity of the metal. So if alpha is 1, means if this is the particle, the solidification front, if this is the front looks like this, then it will just go like this. It will not hamper the position of the particle. The temperature gradient will be like this only, or the isotherms lines, which was said in the class. If alpha is greater than 1, so what will happen? Alpha greater than 1 means the Kp, or thermal conductivity of the particle, is more. So at that, yes, will be more. So at that time, what will happen? All the isotherms, all the temperature gradient will try to come towards the particle, because this is having the most thermal conductivity now. But if alpha is less than 1, what will happen? The particle's thermal conductivity is lesser than metal, so the temperature will try to get uh, will will move from the particles very fast. So it will just go away from the particle because the other region is solidifying, is getting solidified fast, rapidly. The temperature which is dissipated by the all the components, the temperature dissipation from the particle will be slower, and the temperature dissipation from the melted aluminum will be higher if the thermal conductivity is more. So obviously if the temperature is getting lowered down by the melted aluminum, then all the temperature line or the isotherm line will try to go towards the melted aluminum rather than the particle. But if the temperature thermal conductivity of the particle is more, means the heat dissipation from the particle is taking place faster. So all the temperature isotherms or the gradients or wave fronts present over there will try to come to the particles to get solidified, because that is the stable state for the whole metal matrix composite. So is it clear to all? Because this is
Ma'am,
the
what this isotherm means? It is a
okay.
line at which the
Isotherm,
temperature
you
remains
just
constant.
yes, please. Can you please repeat the next second part? You told?
Ma'am, what is this isotherm means? Basically, it is a line at which the temperature remains same.
Yes. So isotherms means you just try to understand with a layman term that if there is one particle and the temperature, if this is the melted region, now the temperature cannot be like, the temperature cannot vary inside the whole melted region. There will be some constant temperature at a constant region. In this region, the temperature will be constant, and the melted aluminum, which is in contact with the mold wall, the temperature there will be something different. So, isotherm means, as you said, along a line, the temperature is constant, but the line is moving towards some direction. The temperature gradient is moving towards some direction because the solidification is taking place now from this. So the isotherms will move like this.
Yes, ma'am. Exactly. I understood.
Okay.
Yeah.
So this
Uh,
is yes.
Ma'am, actually, I wanted to ask Kp by Km actually affects the temperature of solidification, which in turn affects the particle distribution.
Yes.
Uh, Ma'am, like then directly saying that like it affects the particle distribution directly will not be right, isn't it? Like I read it some that like Kp by Km affects the particle distribution.
Yes.
Ma'am, but doesn't it affect the solidification temperature?
Okay, Kp by Km is affecting the solidification temperature, na? Because depending when you heat up something, how that thing will be cooled under normal air, uh, it will be decided by the thermal conductivity of the material. If the thermal conductivity is more, then it can dissipate the heat rapidly. It will get cooled down. So Kp by Km is telling us about the thermal conductivity of this two, the ratio of these two. So if the thermal conductivity is more in one case, so the temperature lines or the just say the temperature which is present inside the mold or the temperature gradient will act like that, na, depending upon the alpha, and the temperature will decide, or the temperature line on the solidification front will decide the distribution of the SiC particles. So this is why you can say the alpha is the determining factor by which you can determine the distribution of the SiC.
Understood, ma'am.
Okay. So the so as I said, so the solid liquid interface is determined by the weighting angle, the surface tension, but the solid liquid, the distribution of the solid in the liquid will be determined by the solidification front. how the solidification is going on, and that solidification front will be decided by the alpha. So as a result, the alpha is the determining factor for the distribution of the reinforcement particles. So this was said that for alpha 1, that is that will give us a planar thing like this one. There will not be any hump in the at the interface. If there is the alpha less than 1, then there will be clustering. Obviously the reinforcement particles will just go and sit over one place because of this uneven distribution. And if the alpha is greater than 1, means all the temperatures are trying to come towards the SiC, so that will engulf the particles more uniformly, or that will help in the more uniform distribution of the particles in the melted aluminum. So this was all about the week 9's lectures. If you have a doubt, please tell me.
Ma'am, there was one sentence like solid liquid interface follows the isotherm of melting point of matrix material. What that it means?
Can you repeat the line again?
Solid liquid interface follows the isotherm of melting point of matrix material.
Okay, so the solid liquid interface, first of all, you have understood how the solid liquid interface is the the distribution of the solid liquid interface is determined by the alpha.
Yeah, yes, ma'am.
Yes. So melting point means the melting point of the liquid, because after the melting point the melting starts, and beyond the melting point the solidification starts, है ना? If there is one solid in the melting, at the melting point the melting will start. So beyond the melting point, that is the solidification, solidified aluminum. Here the solidification is taking place, and there if the melting point, and also the melting point will depict us about the thermal conductivity as well, how much temperature gradient in how much time. So all the things are interrelated and giving us the result of the interface or the distribution of the interface.
Ma'am, it is actually discussing about the melting point of matrix material only.
Yes, matrix material, that's what I'm telling now, the liquid metal.
Okay.
Anyhow, the
But
SiC is not getting, the reinforced material is not getting melted.
okay, means below this means exactly at the melting point the interface will start forming, right?
The melting will start, but here we are going from the reverse direction. We
Yeah.
are coming from a higher temperature to a melting point, and after that melting point, the solidification will start.
Yes. Right. Yes, ma'am. Understood. Because first we are coming
Because
just from higher temperature to melting point.
yes.
So that's what this interface will follow the isotherm of melting point of that matrix material like
Yes,
aluminum,
because we
right?
are cooling down the material. Now, suppose we
Yeah.
were having the 800, not 800, 700 degree. Now we have come to
Mhm.
660 degree, which is the melting point of aluminum. Beyond 660 degree means from 659 or 658, the solidification will be started. And there, this isotherms, solidification front, temperature gradient will play the role to get the proper distribution.
Yeah. Yes, ma'am.
So
Right.
obviously the melting point is the point where the things are getting begin.
Yes, ma'am.
Okay. So this is up to the lecture 9. So you were having a question of non-heat treatable alloys. So whatever I have seen is there are a lot of work present for non-heat treatable alloy. It's not like you cannot melt the non-heat treatable alloy, but the main difference is you can go for heat treatment. Okay, what we do in case of heat treatment? In heat treatment, we go up to an elevated temperature, we hold the material and then we cool it down. And at the time of holding and cooling down, we get the second phase precipitates. The second phase precipitates are properly bonded compounds which are giving us the strength. But apart from the second phase precipitates formation, there are some other strengthening methods as well. If you can recall the second lecture in the week one or the third lecture, somehow around that, there was the strengthening methods. Like if you are adding strengthening means what? The disruption in the dislocation movement inside the lattice. So strengthening can take place by many way. Like if you broaden the stacking fall width, the stacking fall energy will be low, and at that time the dislocations cannot move. Strengthening will take place. If you are adding the solute atoms, which are having reverse affinity, or electronic configuration in such a way that it's just making some dipole inside the material, then the dislocation movements are hampered. That is a kind of strengthening. If we are
Yes, ma'am.
adding some material which are higher in size than aluminum, it will introduce some stress field and the strain field in the, sorry, some compression field and the tensile field inside the lattice. That will lead to the strengthening. So heat treatment may not help in case of non-heat treatable alloys, but these type of phenomena are still there in which you can still strengthen the aluminum alloy. So in case
Ma'am,
of
can you repeat your last sentence? In non-heat-treatable alloys, we are adding the large size of
okay,
particle.
no, I didn't say that we are adding, but I am just first I am pointing out the ways by which you can strengthen the aluminum alloy from the first class. So
Yes,
these
ma'am.
were the thing, na, electrical interaction, modulus
Yeah,
interaction, stacking fall
checking
energy,
for. Yes, ma'am.
dipole energy, or dipole moment, those things, electronic configuration. So those were the
Yeah.
thing in which you can strengthen the aluminum alloy. So now the one, two, three, these things are the non-heat-treatable alloy. So not two, one, three, five. I think these are the non-heat-treatable alloys. I think.
Yes, ma'am. Right.
Okay, one is also not heat treatable, and
Yes, ma'am.
then because one is not having any solute atoms. Okay, so we cannot play with the modulus interaction or electrical interaction, neither the precipitations. So one is typically the not heat treatable. Then come the
Yes.
3 4 5. So 3 4 5 is dealing with the magnesium, silicon and the manganese. So what
Hmm.
happens is when we add the magnesium and silicon both together, we form the 6000 series, which is a known alloy of heat treatable range. So
Yes, ma'am.
because the Mg2Si can be formed as a precipitate, and that will lead to the strengthening. But in case of 345, now the precipitations are not formed. Si itself cannot form any precipitation or the Mg, neither the magnesium. So precipitations are not formed. It's not like it will not get melted. It will get melted. Welding, additive manufacturing, casting, wrought, everything is taking place with the 5000 series, 4000 series. Researchers are doing a lot of work. But there the main problem is you have to go for some other way for the strengthening. You can go for the cold working where you can introduce a lot of dislocations which will lead to the strengthening. We know that you can go for the cold work, severe plastic deformation. There you will get some low stacking fall energy which will again lead to the strengthening. So these are the well known processes of strengthening in case of non-heat treatable alloys. But it's also correct that there are a lot of problem related to the non-heat treatable alloys because after the welding or after the additive manufacturing, you often go for the heat treatments to reduce the residual stress. because due to the repetitive heating cooling cycle and the high power energy density, the residual stress is very high in case of the welding or additive manufacturing. So to reduce that, because residual stress will lead to some hot cracking or cold cracking or fracture toughness related problem inside the material or process material. So to reduce, to get rid of that, we go for heat treatment. So this 3000, 4000, and 5000 series will not get this strengthening by reducing the residual stress with the help of heat treatment. So that is one problem related to the non-heat treatable alloy. So for that, researchers go for higher optimization of process parameter by including more number of process parameter at the time of welding. They set up the welding parameters in such a way that there will be no residual stress present inside the material. Sometimes you need to go with as built conditioned aluminum alloys for few applications. I do not remember the application right now, but there were some uh, automobile application where you have to go with the as built aluminum alloy because of some properties related to the residual stress. So there you can incorporate this type of non-heat treatable alloys because you don't have to go for the heat treatment. So non-heat treatable alloys are having a lot of application and the processing.
Ma'am, yes, ma'am, I understood. In non-heat treatable alloys, just you said, we are not getting precipitation hardening, means we are not having any precipitates when we are heating above a crystallization temperature, right?
Yes.
And we are cooling. So that means it is seen like that, right? Means there is no precipitations in 5000 series. So that's what we are not having for. So it is not good to go for heat treatment processes, because why we are going for heat treatment? Because of the precipitation hardening. We are getting some precipitates at higher temperature, right?
Yes.
So that's what we are not going for these alloys, because we are not having some residual stress, and means the lowering of residual stress as well as some precipitations at
Yes.
higher temperature in these alloys, right? Okay.
And
And ma'am,
yes.
uh, uh, okay, ma'am. Yeah, you tell what you.
So, and another thing is precipitation is also like some compounds which are formed. Now, there is a proper bonding between the compound. But
Ma'am,
apart from, yes,
ma'am, actually, this was my doubt that in 6 series we have Mg2Si, that is a precipitated compound, right? But in case of 5 series, so 5 series, in 5 series also we have magnesium and silicon, but in some less percentage.
yes. So
But
that's
we
what
have,
I was
but
coming to. So
okay.
precipitations means the compounds. But apart from precipitations, we are also uh, well known to the clustering and the atmosphere. If you remember what is atmosphere, atmosphere is gathering of some solute atoms. So the
Yeah.
solute atoms
Yes.
are getting gathered at one place, but they are not having sufficient energy or the sufficient attraction between each other that they can form a compound. So the atmospheres really form inside the non-heatable alloy. Sometimes they lead to some sundering. If you can handle those process parameter and optimize those process parameter in that way.
Okay. Right.
Okay.
Yeah,
Yes.
understood. It is happening, but there is not some particular bond like Mg to Si in case of non-heatable alloy.
Yes.
But there is some atmosphere of the solutes that can hamper the dislocation moment, but but it is not like some compound
Yes.
which is being made, right?
Yes. And
Okay.
also, you go for the heat treatment of non-heat treatable alloys as well. It's not like people do not go for the heat treatment. They do go for the heat treatment, but for other purpose, not for the precipitation. This type of atmosphere you can form. The stacking fall energy, you can play with the stacking fall energy with the heat treatment. with the severe plastic deformation, then heat treatment may resolve your issue of the strengthening. Obviously, the strength of the non-heat treatable alloy can never be equal to the strength of the heat treatable alloy, but it can go around somewhat around the heat treatable alloy strength.
Yes, ma'am. And ma'am, I had one doubt regarding this DSC instrument, differential scanning calorimeter. So in exothermic reaction, the curve was getting down, means the peak was at down position. And in endothermic reaction, it was above that. Means, can you elaborate this? Means, what exactly what we are measuring means we have some two samples. One is annealed samples and another one is strained samples. And just we are giving a power and we are just calculating means what will be the difference in power that is being provided to have the same temperature of both of the sample, right?
Yes. So this
Uh,
is, oh, sorry, this is not intensity, this is heat flow. So it will be said here that exo down or in endo down. So exothermic means exit of the heat, means the heat is released, and endothermic means the heat is absorbed. So here when you increase the temperature, first the heat will be uh, released, and after some time when the temperature will be so high that it will be around the melting or somewhat around the or more above the recrystallization temperature, the heat will getting absorbed. So this portion is very minimum. This is just after the when the temperature is getting higher.
Ma'am, actually, what is this heat flow?
Heat
Means
flow means
between
in
what?
which
Means,
direction the heat is flowing, means whether the heat is released or the heat is absorbed.
okay, so if we have a stained material,
Yes.
so if we are heating this material means we already have some stained energy. Means
Yes.
we already have some strain. If we are heating it, this strain will be released in the form of heat,
Yes,
right?
yes,
So
exactly.
so if it is released in the form of heat means it will increase the temperature inside in
So
case of
whenever
stained
you will
material.
increase the temperature will increase. But as you said, na, the strain is so high inside the material. Means there are so many dislocation moving inside the material. Whenever you will increase the temperature, na, the heat will be released, the strain will be released in terms of the heat, and after some times the temperature if you are still increasing, then the temperature is still increasing inside the material as well, and the heat will start absorbing. Heat will be absorbed, and this is why this endothermic peak you are getting.
Ma'am, and yeah, above this, but we have a peak at low heat flow. So at low heat flow, we have a peak of exothermic, right? So
Yes.
what that it means? Low heat flow, what
Low
it
heat
represents?
flow means exothermics means heat release. Heat flow is towards the outward direction. Heat is released. And also, if you are increasing the temperature, it cannot happen that a lot of heat is released. That will be the adverse effect. Na? So it will be like the heat will be released, and this length will be low, uh, what's it, smaller than this length. This length is the how much heat is absorbed. Obviously if you are increasing the temperature, a lot of heat will be absorbed, but the heat which is being released, this thing will be lesser than the endothermic peak.
Means, ma'am, at that temperature, there will be a 50% of recrystallization. Means most of the
Yes.
means grain has been recrystallized at that particular temperature, where
Yes.
heat flow is minimum. I am understanding. So this heat flow minimum means if there is a strain and we are heating it, then the strain energy is being released in the form of heat. So
Because
again,
at the time of recrystallization, now all the strains we do not really need to release all the strain. you can still accommodate the strain inside the material and recrystallize, because there are the protrusion theory where the high strain region and the low strain region will have a protrusion in between, and there the recrystallization will take place. So
Yeah.
the strain will be released in terms of heat, but it will not be like by releasing all the strain, the recrystallization will take place. No, as you are providing some temperature, some of the strain will be released for certain time, and after that, the temperature will, as the temperature is increasing, the heat will be absorbed only, and the recrystallization will take place. Because you can say that if one material is having a lot of strain, means this material is having lot of strain means extra half plane of dislocation. If it's heated up, then the heat is released at first stage, means there will be no strain, and this is recrystallized. No, that's not the thing. The recrystallization will take place by some other means. There is no relation between this strain release and recrystallization. Obviously, strain release will initiate the recrystallization, but it's not like if all the strain is released, then only we can say it's recrystallized, because anyhow recrystallization means there is no strain present. There are the strain free grains which are newly born.
Yeah. Yes, ma'am.
Understood?
Yeah, understood, ma'am.
Okay. Okay, so that's about it. So non-heat treatable alloys doesn't mean they do not go for the heat treatment. You can go for the heat treatment along with the solutes present inside it, but they will not help in getting the precipitations. But still, they can, yeah, help you in forming the atmosphere and this thing. So that's about it. I have some questions you can see. These are the questions from the current semester week, but as you have said that you are already having the answer of these questions, right? If you have any question from the MCQ test, you can ask me. No question? Did you do this question, solve this question at the time of exam? Both of you? I am asking to both of you. Could you? Okay. I think there is a net issue. Could you solve?
I yes, ma'am. I remember solving this during the assignment.
Okay, you could solve. Good. This is pretty easy when you see all the pictures, because if only one picture is given, then it will be a problem that what it is depicting. But as all the pictures are given, so it's fine. Could you solve it, Sailesh?
Yes, ma'am. I have gone through it.
Okay. Okay. So these are the other questions, and yeah, up to it. So, if you want, I can go with the current semester, sorry, previous semester assignment questions also. Let's do it. So, you just try to answer me fast the questions. Anyone? No one? It's the easiest, na?
Ma'am, one and two,
It's not
one,
correct,
two,
the
and
third
three.
one?
Ma'am, I think the third is also correct.
All are correct.
Yes, all are correct. Then this one,
Still
This
casting,
is
melt infiltration.
and spray deposition.
Yes.
1, 3, and 4. Then this one, which of the following statements are correct about the mail infiltration method of processing MMC?
I think one, two, three, and four all.
Yes.
Ma'am, I had a doubt on the fourth option, fourth part, like uniform structure is
Yes.
achieved.
So
Okay.
why uniform microstructure is achieved? Because when you are pouring the melted aluminum in a preform, now you just imagine you are pouring the melted aluminum in a empty mold. That's what you do for casting. In that case, in the mold world, you will be getting some other microstructure, and in the inside, you will be getting some other microstructure. But here, the solidification is taking place by some other means. By the capillary force, you are getting the infiltration of the liquid metal, because the preforms are present over the whole mold. So the solidification technique in this case is not like the casting. Here, if the alpha is greater than 1, or the alpha is less than 1, or even the alpha is equal to 1, the solidification will be dependent upon the alpha value, and the alpha value is uniform and constant throughout the mode. So the solidification type is uniform throughout the mode, whether it is alpha equal to 1, greater than 1, or less than 1, it will be uniform. So as the solidification is uniform, obviously the microstructure will be uniform.
Yes, ma'am, I understood.
So this is the fifth question. Arrange the steps below followed by the physical vapor deposition. So it will be 1, 2, and then 4. Vapor generation, then fibers are passed through the chamber, and then assembly of the coated fiber. The next one is, in which of the following process or method the high mechanical or electrical energy is applied? It's very easy. It's the high energy high rate. The high energy is provided with a rapid time interval. Which type of processing method of MMC has been used to make this 6061 boron fiber composite? It's a diffusion bonding. Next is, the precursors used to form in situ AlTiB2 composites are. It's the last option. The K2TiF6, it's wrongly printed. It's F6 only, and the KBF4. The liquid does not wet the surface of the solid if the angle of contact is
Obtuse angle.
Obtuse angle.
more than 90 degrees. What are the advantages of the particle which form in situ during MMC processing? It will be the clear interface between particles and matrix. particle matrix bonding will be good, and finer and uniformly distributed metal matrix composite will be formed. The last question is the wettability of the dispersoid in the matrix has been improved by. We have already discussed about it.
Ma'am, it is the first, second, then
डिस्पर्सॉइड के लिए क्या होता है? फर्स्ट वन इज नॉट
It
रिलेटेड टू द
second,
डिस्पर्सॉइड ना.
second, third, fourth one,
yes, ma'am. Second and
and
third.
fifth one,
Second, third, and increasing the
fourth.
processing temperature of aluminum, because it will affect the temperature gradient, the melting and those things also, and disruption of aluminum oxide layer form on dispersoid surface. So yeah, that's about it. If you still have any query, you can ask me.
Ma'am, actually, there is a query from the current week's assignment for the this semester. Ma'am, actually, in that there is a question regarding the the solidification temperature and the thermal conductivity. Thermal conductivity has an influence on melt temperature, particle distribution, particle bonding, and melt solidification. I had read this in place, and I feel that it has to be two answers for it, and it's a single choice. I don't know what to do.
According to you, what will be the answer?
Ma'am, I feel that melt solidification and particle distribution are two answers, but I
Can you
don't know
repeat the
if
question again?
the thermal conductivity ratio has an influence on melt. The options are melt temperature, particle distribution, particle bonding, and melt solidification.
And the real answer is the distribution.
Yes, ma'am. Ma'am, but I know that it's distribution, but shouldn't it also include melt solidification?
Melt solidification means
According to me, the solidification of the particles inside the melt and the temperature, since it's dependent on the temperature, shouldn't it also be included?
it only influence the uh, solidification type. So, according to the solidification type, the distribution will be hampered or the distribution will be affected. Neither the interface, because the interface will be depicted by the surface energy, surface tension, angle, those things, and the solidification itself will dependent upon the melting point. The thermal conductivity is playing the role to affect the distribution only. The alloys are having different melting point than the pure metal, but the mmcs do not. Yes, mmc will the melting point will be hampered by the mmc obviously, because there is some temperature gradient due to the alpha, because the but the effect is not that much like the alloys.
Yeah, ma'am, I understand.
Yes, the alpha is playing the role just for the distribution purpose.
Okay, ma'am, I understood.
Okay.
Thank you.
Okay, then we can stop the session now.
Okay, ma'am. Thank you.
Thank you. Thank you. Good night. Bye.
Thank you, ma'am.